Okay, welcome everybody to the Society of Wetland Scientists webinar today. Thanks for joining us today. And we're going to get started. My name is Gordon Shaw, and I'll be the moderator for today's presentation. Today, just wanted to introduce a few things here before we get started on this. This is put on by the Society of Wetland Scientists webinar series. To learn more and to find out more about the Society of Wetland Scientists, you can see some of these reference resources that we have on here through Facebook, YouTube, on X, and LinkedIn as well. You can go to the website, the Society of Wetland Scientists, and you can find webinars, including a copy of this one we published on there as well. You can see past webinars at these locations. Some of the upcoming webinars that we have are located here on this schedule. We've got September 19th coming up, the Sackett Symposium. We're going to have a topic, a presentation about that one. And then after that, for the Spanish webinar, we're going to have one on September 25th, a Who Mentored program. And then you can see the other ones as well. October 17th, anthropogenic impact in wetlands. I believe that's in Africa, and that's an international webinar. And then we've got another couple coming up to be determined in December, but also we have another one, PhD, on December 19th, PhD findings on floating wetlands. Some of the sponsors that we have for today's webinar include Cattails, Environmental LLC, and Davy Mitigation, and EcoBot. We encourage you to go to their websites, go check them out and see what resources and opportunities they have there. We're grateful for their support in this webinar series. A couple of housekeeping items I want everybody to be aware of. If you have a question during the webinar, please put it in the Q&A box at the bottom of the screen. And then we'll answer those after the presentation. If you have some kind of technical difficulties, please enter those into the chat box. And then for the survey, following the webinar, an email survey will be coming to you. Please complete that and return that to receive your certificate of participation, and then to provide any feedback you may have as well on the webinar today. Okay, I'd like to introduce the speakers for today's program. Today is pre-production plastics remediation and restoration in the coastal zone. And our presenters for today are Ryan Fikes and Blake Simon. They're from Freese and Nichols. Just to give you a little bit of information about these two gentlemen. Ryan is a trained biologist with expertise in coastal ecology and habitat restoration, and he brings 15 plus years of experience providing scientific expertise to identify and evaluate restoration projects in the Gulf of Mexico, and to ensure investments are scientifically sound, integrate with other projects, and achieve realistic outcomes. Through management of strategic partnerships, Ryan has worked to leverage existing resources to promote and facilitate innovative approaches to conserving ecosystems and their resources. Ryan has expertise in advising state and federal leadership on issues associated with the effects of oil spills on habitat and wildlife, and has assisted in evaluating the merits of both state and national restoration plans. He's worked over the years as has centered around connecting science and policy and evaluating, sequencing, planning, and implementing large-scale ecosystem restoration efforts. In addition to Ryan, we also have Blake Simon, also from Freese and Nichols. And Mr. Simon has 12 years of experience in the environmental field, working for the National Park Service, Bureau of Land Management, APTIM, and Freese and Nichols. He has spent 8 years working as a wetland scientist assigned to the coast-wide reference monitoring system in southwestern Louisiana. And Mr. Simon completed a Master's of GIS program at Penn State in 2022. He currently flies drones, creates maps, and builds GIS web applications for Freese and Nichols. So I'd like to turn the time back over to Ryan. Ryan, you want to go ahead and share your screen and take it away?
Sure. Thank you, Gordon. Let me go ahead and get that going here. All right. Can y'all see my intro screen here okay?
Yep. Looks
Perfect.
good.
Well, thank you, Gordon, for the introduction. Thank you, everyone, for joining during your lunch hour or around your lunch hour today. Again, my name is Ryan Fikes, work for Freese and Nichols. I'm based out of Austin, Texas. Blake's based out of Lafayette, Louisiana, and we work for our coastal and environmental team in the southeastern U.S. Freese and Nichols is a civil engineering and environmental science firm, consulting firm, centered really around work revolving in water. So everything in and around water, including our environmental and coastal landscapes. And we're really excited to be able to talk to you today about a pretty innovative project. It's the first of its kind nationwide. That's a, kind of full-fledged remediation project around pre-production plastics. So, and we're talking about the coastal zone. I know originally the presentation said riparian, but we're actually going to talk about both riparian and estuarian as part of this presentation today. So a couple of different wetland systems. So to get us started, I just kind of wanted to give some context here. So, again, we're talking about pre-production plastics, so the base kind of element of plastics as it's finished at the manufacturer. And when you think of incidents in the past few years, like the massive nurdle release in Sri Lanka, that brings to the forefront this issue around releases, consumer waste, and kind of the global issue that it presents. And so community awareness is really heightened in this decade, especially in the past few years, and that's resulted in a number of things. One, new regulations and things that we'll talk about, but also emerging programs focused on reducing plastics and now remediation efforts centered around cleaning up and restoring systems. Another thing that's really emerged is citizen science efforts. There's a couple that I've thrown on the screen below, and these are also programs from manufacturers themselves, but things like Operation Clean Sweep, Great Nurdle Hunt, Nurdle Soup, some of those things that have online platforms in which that citizens can go out and document plastics, plastic pellet or nurdles that they find in the environment. And so we're pulling in some of that citizen science data as we navigate this emerging area. And then we'll also talk about regulatory in terms of new permits. So the case study we're going to talk about today is based on the Central Texas coast and in Texas, and working with the Texas Commission on Environmental Quality. New permits are all moving towards a zero plastics discharge, and we'll talk about what that really means in terms of practice. And for anyone that's ever worked around discharges, if you think of environmental contaminants, chemicals, heavy metals, there's never a zero discharge. There's always some tolerance threshold. And so when you move to a zero discharge, even though you're talking about, in theory, an innate element like plastics, that can create some real issues. So regulation on the Texas coast, just because we're a little on the forefront of that, Texas and California, what do pre-production plastics discharges look like? We have them in both cases on the case study we're going to talk about today, stormwater and wastewater. So stormwater discharges going directly from a facility versus wastewater discharges going through whatever wastewater treatment system that has. Sometimes those result in an effluent into a fresh or saltwater system. In our case study, we're going to talk about it going into a bay or estuarine system. We know that permit violations can be triggered, in particular Clean Water Act fines and penalties, and resulting remediation actions required as part of those Clean Water Act fines and penalties. And as I mentioned earlier, in Texas, we've got this commitment to zero discharge for new permits, but also following a Clean Water Act violation in the case that we're talking about today, our client is actually committed to a zero discharge. But there is no regulatory cleanup or regulatory standard for cleanup, and so we're really trying to kind of set the stage for what that looks like in practice, which allows a lot of flexibility for Blake and my team in working on this, but we're also trying to set future precedent for what these regulations look like. And then some of the court-ordered requirements, one of which we're focusing on today, which is the remediation piece, but there's also engineering and monitoring side of things. So facility retrofits for bringing in engineers to try to eliminate future storm and wastewater discharges, and then monitoring to determine if there are new release and what might trigger subsequent new fines and penalties. And this is a good moment for me to say, when we talk about this today, I'm going to speak about this project in a little bit of generality. So this project is litigious in nature. It is operating under a federal consent decree, and it is in litigation. So everything that we're doing is operating under a federal court system. So I can't speak to the specific client or place-based location of the project, but that's really not the important part here. The important part is, how are we navigating a project like this? How does it influence future policy? And how are we doing the remediation and learning from it? So a couple things about this kind of landmark lawsuit that governs this project. The key thing here, first and foremost, is it is not just addressing current releases of plastics, it addresses legacy releases. In the case of this project, 3 decades, 30 plus years of releases into the environment, which makes things very complex. There's also a monetary settlement outside of the Clean Water Act fines and penalties governing the restoration work that goes into a trust fund. These are those subsequent new releases that figured up to daily fines. And then, as I mentioned on the previous slide, this case, the defendant has to retain all 3 of these specific roles: the engineer to stop discharges, the monitor to identify discharges, and then Freese and Nichols, who is brought on as the remediation consultant to clean up the actual plastics released by the manufacturer. And then the last that I'll mention here that really kind of governs our work and makes it a little complex is that is an all parties involvement case, meaning that every step along the way, every action, every approval requires both the plaintiffs and the client in order to keep moving forward, and that there is no ex parte communication allowed, meaning I can't talk to the client without having the plaintiffs privy to the lawsuit as part of every email, every dialogue, even every text message. So definitely makes things complex in terms of how you are even communicating simple functions within a project. And we're doing this across these 2 remediation areas. Phase 1, which is where I'll focus on the presentation today, which is 4 miles of impounded coastal stream, this riparian habitat, and then phase 2, which is about 75 miles of bay and estuarine shoreline. So what are we trying to do here? So the consent decree and the remediation consultant requirements are these kind of 4 main pieces. We had to develop a remediation plan with this goal of removing most plastics from the environment while protecting ecosystems. And I underline those 2 components because they're important, but yet very ambiguous. So most plastics is not defined. And so Freese and Nichols came in, and one of the first things we did is said, what would we want to be effective? And we decided that an 80% cleanup, or anything greater than that would be considered most from the environment. Give ourselves a realistic objective to tackle. And then what does protecting ecosystems mean? That can mean a lot of things for a lot of people. This is going to tie into kind of this next bullet here, which is determining what removal methods will cause significant environmental damage that cannot be remediated. So we have no monetary ceiling to the project. We're supposed to go in and clean most plastics, but we also decided, given this cause, that we wanted to try to make the system better than we found it. And so if we're going to go in and damage an environment, we're going to make it better than we found it. Some other things here that are important: we had to develop a methodology for estimating the weight and volume of the plastics themselves that were removed, but that has to be on a daily basis. So that makes for the need for real-time analysis important. And we have to continue the cleanup within these systems until we, the remediation consultant, determine that most have been developed and that further actions will harm the ecosystem. So let's talk about the challenges with that before we jump into the technology and approach and hand it over to Blake. So, obviously plastics are there are mobility challenges around them. In the case of the plastics we're working with are 2 types, polyethylene and polypropylene, which means that luckily these plastics float. But that does mean that they are more prone to movement during storms and extreme weather events, aeolian transport once they're out of the water or even on the surface of water in calm systems. Currents, tides, and other circulation patterns within our bay system. And then in our creek system, given that's an impoundment, meaning that they're changing water levels based on draws and usage within those containment ponds, and that impacts their mobility. And then one that was really, really important, kind of the most important, that was not an obvious one for Freese and Nichols and our team, is livestock and wildlife. And so that image on your right there of a cow along the creek bank looks, pretty benign, but 30 years of farmlands along the creek system in which we're working in, those 4 miles of impounded stream, are almost all ag lands and all active ranches. And over 30 years of cattle going down to the creek banks, they've pushed plastics, anywhere from 6 to 24 inches down into sediment. So it no longer became a just surface cleanup in the water. We're talking about plastics impacted soil up to 2 feet deep along the banks of these streams. And I'll get into more of that here in a little bit more detail. And then during actual remediation, just vehicular and machine traffic moving things around, given their lightweight nature and mobility to be able to be blown around on the surface. Again, I mentioned that we're talking about 2 types of floating plastics, but they come in 3 different forms as manufactured in most places in the United States. Pellets, which are your typical nurdles, as most people hear the term, but also shavings and powder, which are much smaller, more lightweight, and much harder to collect. Luckily, in our creek system, we're only talking about pellets, but in our bay and estuarine system that I'll mention a little later in the presentation, we're talking about all 3 of these elements, which makes remediation quite complex. I mentioned already that we have 30 years of plastics, but that there are ongoing releases in our system. So since the time that our remediation activities began in our creek system, we've had 11 new releases, bringing new plastics into the system, again, making it more complex, meaning that in areas where we've already done remediation, you have the potential, and sometimes a high potential, for recontamination. And then a range of habitats that I have listed here, many of which I've already mentioned. Technology is really important. It's a part of the work we're doing in terms of assessing and developing new technologies. Just wanted to show this briefly, and that there are a lot of things out there, but they're primarily on the collection front. So once they've already entered the ecosystem, and how are we skimming, collecting, dissecting them out, there's a lot less on the prevention side, and ultimately that's key in terms of where we're going for both stormwater and wastewater, but the science is kind of still out. So quite the imbalance here, and I think important as part of this conversation. Freese and Nichols has worked with a number of different technologies, but one I wanted to mention in particular is Hula One. They're based out of Quebec, Canada. And these are just some examples of some of the equipment types that we've actually kind of worked on. Again, these are all primarily in our base system, with the ability to siphon out plastics from surface organics, sand, and other types of sediments. But these really don't get to that embedded plastics component that I mentioned in the creek systems, where you're working with things such as blackland clays and really sticky sediments, where it's a lot harder to just kind of siphon and turn things out. So the meat of what we're talking about today is this. This is the comprehensive approach that Freese and Nichols has worked over the past 4 years to develop on this project, and hope to carry forward on many others. And it all starts with looking at that historic plastic data. So citizen science data, from things such as Nurdle Patrol, which is based here in Texas. Jace Tunnel out of Hart Research Institute at Texas A&M Corpus Christi leads that efforts. But also previous cleanup contractors as hired by the manufacturer prior to Freese and Nichols coming on board, and prior to the Clean Water Act penalties. And then we've got our wide-ranging plastics assessments that I'll discuss, that included both comprehensive and preliminary assessments, collected both qualitative and quantitative data on both the surface and subsurface for those plastics impacted sediments. We apply a lot of different screening to the work that we do. So sensitive habitat, whether that be critical marshes in our estuaries, or legacy oaks and other sensitive tree species in our freshwater or creek systems. But also have to look at things like armored shorelines, landowners, and elevation when we're working in our remediation zones. And ultimately, that is all done to land us on remediation boundaries, which we have 2 different terms for. In our creek system, and this is where Blake's about to jump in and talk about how we do this, we assess and identify areas of concern. And in our bay systems, we look at high probability areas. So kind of areas that are a little bit more ambiguous, given the large scale nature of bays and the more dynamic movements within them. And I do not expect you to be able to see all the words on this, but I just kind of wanted to show example of some of the decision support frameworks that we've developed here at Freese and Nichols, because it's not just about whether plastics are present. It's about things like abundance, whether they're high or low, and give you prioritization mechanisms for tackling those, but also bringing in those mobility factors. So we prioritize areas that have a high mobility scoring. In other words, places where during a weather event, plastics are more likely to be redistributed around a system. And then kind of tertiary lens to that is accessibility. So if we can use large scale equipment and mechanisms for removal, we can target those areas, whereas places such as around sensitive habitat, we have to do a little bit more of a kind of fine-tuned precision removal. That's not as efficient, even though it's critical, but those are a little bit further down in terms of prioritization. And they ultimately land us on both the ranking and also the remediation actions, which are kind of represented by the red squares on your screen, of which there are kind of 5 different ways that we tackle those in this project. So I'm going to hand it over to Blake at this point in time. I'm going to stop sharing and let him take over the same slide. Blake, I'll go ahead and give it to you.
All right, let me pull that slide up.
And appreciate you guys dealing with us as we do these transitions. This is a huge project with about a team of 50 folks on it. Blake is leading everything geospatially on the areas of concern for this project, and it's really a critical component. So I'm happy to have him join me here today.
Now. Okay, can you see that okay?
No, we cannot see anything right now.
Right. Okay, is it sharing now?
Yes, sir.
Okay, great, thank you. All right. So thanks, Ryan, for that introduction. So once we landed on a general area for the remediation, where it would take place, we then need to focus on what Ryan talked about, these areas of concern, or AOCs. So these facilities have water outfalls attached to them, and they lead to the creek system, but you can't just concentrate on those areas. There are other criteria that have to be taken into effect. So one of those is the habitat sensitivity. The other is plastic abundance, where we used heat mapping and other GIS tools to determine these areas. Ryan spoke of the mobility of the plastics based on where they are, higher up or close to the water. That makes a difference, and also the contractor accessibility. So how are you going to move this large equipment into these areas and out of these areas safely and efficiently to where you can remove these plastics and you have room to do that. So initially we developed a threshold of in excess of 50 plastics per cubic foot. And I think Ryan mentioned that was with the goal of 80% plastics removal. And also a mobility score was given to these plastics. And then it was during the project, quickly we realized that this would have to be changed, mostly because of the mobility of the plastics. So we went from that original 50 for the whole area to dividing it into 4 zones. So there's zone 1 above the ordinary high water mark. Zone 2 is from that line to the water system. Zone 3 is within the water with emergent vegetation present, and zone 4 is just open water. So each one of those has a different threshold associated with it. And this is our remediation cycle. Because this was a federal consent decree, Ryan mentioned both parties must sign off on everything and be included on everything. So between each one of these steps, both parties are involved. So it starts with the plastic removal, then it goes to an inspection with all parties. The backfill is brought in and stabilized. And then there's the vegetation restoration aspect of it. And that's followed by 6 months to a year of vegetation maintenance. And then there's a final all parties inspection before everything's okayed. And this takes place for every one of those areas of concern, or AOCs. And while that's going on, and after all those steps, surface cleaning is taking place also. So this graphic is basically showing the 3 steps of our remediation process. There's the confirmation step, there's the excavation with the excavators, and final restoration. And you can see those zones represented on the bottom half of this graphic, zone 1, 2, 3, and 4, just kind of giving you a better idea of where those are located. So we talked about kind of the methodology and what does that mean in terms of this particular project. So it was on an impounded tidal creek. There were 350 acres of fresh water, 9 miles of shoreline. It included a wooded riparian zone, and the littoral community was low in diversity in this area. And then the actual plastics removal, it was 48 acres of the actual area of concern, and 30 of those acres were above the ordinary high water mark. There was vegetation removal from the creek system. And then, as I showed you in some of those graphics, the soil excavation by the excavation crew was done from 6 to 24 inches deep. And that was based on exceedances of plastic counts. And then finally, surface cleaning, once again, throughout the whole process, and after this process is done, that continues. All right, so you have all this data, you have thousands of points, you have polygons, and it's really important, and you have multiple people working on this project. You have our field crew, you have the subcontractors who are excavating, and you have, even more important, the project managers who are making decisions daily, and those decisions are carried on throughout the process, and they lead to more excavation or moving the equipment somewhere else. So it's a very expensive task, and you can't get that wrong. So it's important that everybody has access to that data. So we use 3 applications and drone imagery to actually make that happen. We use, they're all Esri applications. We use field maps for the field crew to gather points and information and to kind of guide them along the way of the different depths and the thresholds. Then that is updated in real time to a dashboard, and the project managers can look at that. I'll show you in a second. They can use filters and make decisions in real time. And then we have a crew of GIS analysts who also take that data and create some high quality graphics for multiple parties and internally and for different methods. And I mentioned the drone imagery is kind of used throughout this. We perform a monthly drone flight over the entire creek system. All the AOCs are mapped. We generate an orthomosaic. We can pull elevations from there, and those monthly drone imagery is used throughout everything we do, everything deliverable we produce, basically. So here's an example of one of the AOCs. This is a drone video from the site. So there's the area of concern. You can see our field crew digging right there. They actually find this boundary by using a highly accurate, like a GPS receiver, and that's connected to that Esri application called Field Maps. And along this red perimeter, they dig samples, and those green flags represent samples that did not exceed the threshold. And then this red flag is an example of a sample that exceeded the threshold. And when that happens, we step out and there's an expansion that happens. So this area can actually grow, and you'll see shortly can shrink also. And I'll go to the next slide. This is a video of our field crew member using the application. So here's kind of a screen recording of field maps in action. You can see they see all the points. The colors represent if there was an exceedance or not exceedance, green and red. So the goal here was to try to reduce the number of errors on the back end. So, these are really long field days. It's really hot out there. It's easy for someone to type in something wrong or to make a mistake if you're taking 100 points in a day. So you want to give them only the options that they need to see, basically. So you see choosing the zone right now, the type of sample, and based on these selections, the further options that pop up are only related to those previous groups of questions. So this data will be sent exactly to the place it needs to be. And when this yes no question is selected, you can see that exceedance field is actually auto-calculated. All this is being run in field maps through some custom coding in a language called Arcade, which is a kind of Esri specific scripting language. So that is then updated to ArcGIS Online, and it gets shared to a GIS dashboard and also to the GIS analyst in the group. So everybody sees everything in real time as soon as it's taken.
Blake,
Yes.
I'm sorry to interrupt. You're really choppy. I don't know if it's your headset or not, but
Oh, sorry.
so
Is this
that
better?
whatever you just said
Mm-hmm.
was very, very choppy. So I don't know if you want to go back over it or not. I
Sure.
apologize.
Yeah, can you hear me okay right now?
Whenever the video is playing at the same time, it's logging
Okay.
things up.
Okay. Yeah, I'll just explain without playing the video. Basically, the field crew member, you want to give them as few choices or as few chances to make an error as possible within the data. So it shows them only what they need to see, and all that is being driven by a scripting language through Esri called Arcade. So it's custom coding on the back end. And based on their selection, it only shows them the important next question. And based on that question, it only allows them to input values related to that data specifically. And I'll stop from playing this 1 second, but this is an example of one of our GIS analysts in one of the offices. And she's working on the project right now. And as part of this, we generate all kind of different figures and graphics and map books to go along to the different parties and to the client. And let me play the video. Here's some examples of it. You can see tree canopy represented. And these are the different excavation zones, sensitive habitats, and a basic AOC with expansion shown. And I'll take a pause right here to just explain what's going to be shown right now in case the audio is breaking up. So the final step in the technology trio is the dashboard. And this allows the project managers, as I said previously, to see all that data in real time. They can filter things. They can select only what they want to see. They can get counts in real time of how much has been taken the day of, the previous week, and they can also have ability to access multiple drone imageries at one time and swipe between them and make a comparison between those two things. And I'll just play a short clip of this video. So this is a dashboard right here. You can see all the points are represented. And the filters at the top are date range, exceedance, and they can select categories. And I'll skip ahead a little bit. And you can select, restart the video, that's okay. So here's an example of that drone imagery comparison tool, where there are two dates on screen, and the project manager can actually swipe between different drone imagery and see the changes in the site, which you'll see. So here's a static image, and on the right side, you can see two types of sampling we do. It's drop sampling in the creek itself, and more common perimeter sampling upland from the creek. And you can see the red points represent exceeded confirmation samples. And in that case, the yellow line represents an expansion area. So this is actually an expansion of what will be excavated in that area. So you expand until you hit a non-exceeded sample, basically. This is another graphic showing how some of the excavations are represented. You can see that kind of light blue color with the red square on it. That's one of the samples that is exceeded. So that area gets an additional 6 inches of excavation, and the surrounding area with the clean samples stays as is. And on the left side right here, you can see different number of depths we actually do, and we provide the area of those depths of excavation to the clients. Some AOCs can get really complicated. Some are very simple. It just depends on the samples we take and the layout of the site. This is an area I talked about earlier where AOCs can actually reduce in size. So you see all green samples within the red, and it's shrunk down to only the area with the red samples. So that does happen sometimes where there's a reduction in size of area of concern. This is basically a plan view showing the proximity to the shoreline and the water, and showing the excavator depositing soil into the in-dumped machine. And there's one more video, so I'll let it. So the purple boundary right here is representative of the AOC that's already been excavated. Besides the Leica devices we use and the technology, the Trimble devices that the subcontractors use, their equipment is also loaded with very highly accurate GPS devices and antennas, so they can get to exact depths and stay exactly inside the area of concern, which is needed in this project. And then swing around to here. So the excavator has excavated this portion, and this is the remaining portion of the AOC to be excavated. And at this point, I think we're going to transition to the restoration component of the slides. So I'm going to hand it back over to Ryan.
Awesome. Thank you, Blake. Let me know if folks can't hear me well. And I do appreciate y'all bearing with us there. I love all the drone imagery and videos that Blake put together for that. Sorry if it clogs up bandwidth and results in some choppiness. So wouldn't be a good webinar without some kind of technical difficulty, right? So I do want to just say a couple quick things, with what Blake just showed, in case it wasn't really obvious, and especially given that this operates under this, consent decree and with a lot of legal scrutiny on it. With these packages that Blake was showing that have to be developed in all of these figures, happen very quickly, and so any given AOC, from the time you do the sampling, identify what needs to be excavated, complete that, backfill it, and then complete the at least cover crop on it, happens within about a week period and has 2 different approval periods and 1 site inspection. And so if you had to collect data, wait to put it on a thumb drive, drive it back to an office, multiple hours away, have it reevaluated, make tweaks, and couldn't do that in real time, it would slow the entire process. So this real-time coordination between field offices and then our offices with our geospatial analysts has saved the client a lot of money and a lot of time on this project, and really kept from potential contamination, because you don't want to keep those cuts open after they've been made any longer than you have to, and run the risk of plastics falling into those and then reburying it and basically, negating the entire issue that you were trying to fix there. So thanks again, Blake, for showing that. I just kind of want to show the second half of this, which again, Freese and Nichols was really trying to make sure that, as I mentioned, we were including the restoration component. We have a lot of ecologists and biologists on our team that really, thrive in the restoration space, as I'm sure many that are joining us on the webinar here today do. And so we really wanted to take advantage of, enhancing biodiversity and bringing back some of the native plants, as well as soil within these areas. And so once the plastics had been removed, we really wanted to make sure we were bringing in locally sourced fill and native topsoil to enhance, the likelihood of success for some of our revegetation efforts. We also wanted to make sure we were reducing any kind of erosion potential. So BMPs are put in place, everything from a 2-to-1 slope ratio going into the creek itself, stabilized with straw wattles, and then with hydro-seeded cover crops immediately following backfill activities in order to really minimize that erosion potential. And then coming in with the revegetation efforts to try to get back to a more natural or native condition. Again, given the fact that this is an impounded creek system, it's never going to go back to that same fluvial, ecosystem that it was previously. It has been highly modified, but at least enhancing native biodiversity could be achieved on something like this. So getting back to that grassland savanna and the uplands versus, a lot of invasive mott's, things like hackberry and others, and then below ordinary high water, increase those natives and biodiversity of aquatic veg. Not going into a ton of detail here, but just kind of describing how we did this. We've got that native seed mix for hydroseeding. If it was in the winter, that was a temporary cover crop with things such as winter rye dominating the seed mix, and then a more permanent one done in the spring or fall. But then we also installed mott's and understory vegetation at about the rate of 1 per acre. So given the width of the average AOC, that put the mott's about 300 feet apart, with a 10 tree minimum and a 30 shrub minimum per mott. Everything upland required a 1-year maintenance period, and was considered successful and could include maintenance planting events to get to an ultimate 80% survival at the end of that 1 year. And the way we did this, it's a little different than norm, is the survival percentage was not just the number of surviving over number of planted like you would typically see. In this case, again, this is because of the kind of federal requirements. What was required is the ultimate factor. So we could overplant in this case to enhance the likelihood for success. And so the number of surviving over the number of required is what was used to determine the percent survival, giving us some flexibility as we did overplanting seasonally. And we did this both in the upland and also in the littoral zones. And so down in the littoral zone, we had 3 rows of veg at 6-foot spacing, different lists of species per each of those 3 rows based on the inundation factors, and also the water levels at the time of planting to maximize success. Bottom right image there shows an example of some live stakes, such as black willow, that we put in about every 100 feet of clusters of 3 to 5. And then did a lot of invasive species control, some at scale with hand removal or actual mechanical removal through excavators, but then also ongoing maintenance and herbicide treatment plan that's continuing to be applied throughout the kind of life cycle of the project. And that littoral zone only had a 6-month maintenance period, but with similar 80% survival requirements like the upland savannas. Just quick photo here, one of the areas that we're really proud of. This is 23 versus just earlier this year. Sorry, I don't have a image of this, what it looked like in native state, but I would have had to traipse through a lot of thorny vegetation and invasives to get in there. But the key thing is, we've really stabilized these shorelines. We've got a lot of native wildflower mix put in here. We've got cactus, we've got trees that are going to be coming in, about 15 different species of trees that will ultimately create a lot more bank stabilization along this creek shoreline. And Blake mentioned this earlier, but all of what we've been discussing is in terms of those excavation activities were part of that removal for plastics impacted soils. And just as important are those surface plastics that basically impact the entire creek system. And there are 2 things that have been happening. One, during excavation activities, while you do have other BMPs such as silk curtains and booms around the active remediation areas, you still do get some exiting of plastics out of that, especially during high wind events where you've got waves kind of overlapping booms or sets of booms, and these plastics are highly mobile and float on the surface. So surface cleaning has been an ongoing thing, but once all remediation activities for the plastics impacted soils are done, the ultimate goal is to establish one final surface plastics threshold. That's what we've been working with right now, is working on getting an approval of a 10 per square foot threshold. And we'd be working section by section on the creek, north to south, making sure that everything on the surface is finally cleaned, doing those all parties' final inspections, and then getting the surface component of this remediation effort signed off on. So this is just one of those decision metrics that I mentioned earlier that we use to help us get to those all parties inspections. And so this is the key here, what we've gotten to date. This is over 1.5 years of active remediation in that 4 miles of creek system, and we're not done yet, but more than 10,000 samples collected in the field that Blake has been managing, which has led to the removal of about 42,000 tons of plastics impacted material. All of those have a subset that are sent to a lab in Houston that painstakingly go through and dissect a gallon of material and pull out every bit of plastic, weigh it, count it, and extrapolate it. And so that 42,000 tons of material has resulted in the removal of just over 3 billion plastic pellets from the creek system. And while we're really excited to have that level of removal, one thing that I'm sure is very obvious to everyone as you're looking at this is what's happening to that soil. Why do we have to send it to a landfill? And this goes back to that lacking technology component that we're all wrapping our heads around right now, which is there's not an easy way when working in these soft clay systems to really mechanically separate soils and plastics without it taking 10 times as long and costing 10 times as much money. But ultimately, we'd love to be able to leave that out there since the soil itself is not contaminated. We just need to pull out the actual contaminant, meaning these isolated plastic pellets themselves. So that's the need. That's kind of reiterates the need for that kind of continued technology development component of this project and any future efforts. I wanted to take just a few minutes here before opening up to Q&A to talk about our phase 2. So everything we've been mentioning so far has all been really for our freshwater creek system, and that's phase 1. Phase 2 moves out of that creek system, which is represented there on the kind of left of your screen by that kind of make-believe, manufacturing facility, and leads us out into the estuary. And for the project we're working on, as we mentioned earlier, we have about 75 miles of shoreline we're dealing on the mid-Texas coast. And so we followed that same comprehensive approach to plastics assessment and setting up remediation areas as we did in the creek with some modifications. One of the things that we realized really quickly in both our kind of qualitative surveys and then our quantitative sampling is that we weren't dealing with quite as dynamic of an issue in terms of vertical distribution of plastic. So in the creek, we have plastics impacted soil and those surface plastics. And that's mainly because of the ag land and the cattle pushing things into the soil, and also things such as wild hog. On our bay shoreline, where we have a little bit more consolidated sediments, wetlands, and kind of beaches and shell hash, we do not have that same impaction issue. It's a surface plastic issue. And so we're not going to be doing any digging, but of course the scale and the mobility component is a lot more complex when you get into the bay system. So we've done similarly, developing pellet concentration hot zones. It's just kind of depicted by the image here. Applied different screening criteria such as bay sensitive habitat analyses, armored shoreline analyses, which obviously impact things such as distribution modeling when you have places where you're not getting depositions of plastics along the shorelines. And along the way, doing all those assessments, what we found that was most important, and again, this is another one of those aha moments, was every time you find those plastic pellets, they are not surprisingly always found with rack associations. So anyone that's familiar with bay shorelines or any kind of interface, you've got these rack depositions based on the most the latest high tide or storm surge or hurricane event, where you can see this very clear line of demarcation where the most recent rack deposits were made. And so what we did was, as part of our kind of comprehensive qualitative sampling, was determine where those elevation benchmarks at the time of sampling were and in which rack lines were they associated with. And so an example, Kelsey Calvez on our team there on the image to your right, going out shooting those along those high and low rack lines where plastics were identified, and helped us develop what's the scale of what we were looking at. We then went in and decided what kind of threshold we were really modeling around, which in this case was a 10 plastics per square foot threshold, and used that to develop a series quarter mile by quarter mile, like you see here on the right, which is what is the area that you have the highest probability for plastics distribution. And those are what we call HPAs, or high probability areas. And we have those for every quarter mile section around the 75 miles of bay shoreline. We can rerun that modeling with shooting some simple elevation benchmarks and using existing LiDAR data to remodel after any storm event if we do have a higher or lower rack distribution, and then use that to kind of guide cleanup efforts. But there are a couple of other things that we have to take into effect with that, so we can identify where the rack is, but this is typically deposited higher than the ordinary or high water mark. So we're going out of the public domain and we're going into the private domain, meaning we've got to deal with landowners. There are about 250 plus landowners in the remediation area that we're working on in this estuary. So we're having to actually phase those activities out into a pretty detailed landowner engagement plan and strategy that'll be implemented over the next couple of years. And in order to keep some progress moving, we've kind of developed 3 phases within our Bay approach to, what are those currently publicly accessible lands like city, county, and state lands, including the state submerged lands like the image that I showed you on the previous slide. And then phase 2 are those private lands that include multiple quarter-mile HPAs. And then the final kind of phase 3 will be all of the remaining with individual landowners, which are homesteads, vacation homes, estates, or small corporations or businesses that exist around the Bay themselves. And so there'll be a pretty intensive strategy because each one will require sign-off, access agreements, et cetera, to get on to remove the rack and associated plastics from their properties. In order to get to that point, we're doing reassessments every year or following any kind of significant weather events in which we have a series of thresholds established, which could include a high wind event, hurricane, tropical storm, or a quantifiable release from a spillway or the river system that empties into this bay. And then we're doing some pretty intensive rack weight and volume estimations to wrap our heads around what is the known amount of rack within a bay system, what is the amount of that that's impacted with plastics, and if we had to remove it, given the lacking technology around plastic separation, what does that look like in terms of a quantified volume and weight of plastics impacted material that you have to remove off 75 miles of bay shoreline? This is my last slide, and I'll stop here and we can open it up for Q&A. But where does that leave us on this project that's still underway, but trying to set kind of a benchmark for future efforts? In the creek system, where we're really wrapping things up for those plastics impacted soils and restoration, we're in that long-term monitoring phase beyond just what was required as part of the contracts and that 80% survival. It's what does it look like over time? Do we see new emergence of plastics? Are we identifying places where our modeling and sampling missed? And how is that going to influence future policy and regulations? Not just in terms of permits for wastewater outfalls, but what about regulations for cleanup standards or thresholds as EPA and state agencies think through things? And then how do we work with other technology groups to develop more efficient and effective systems for separating plastics out of organics and sediments so that we can have less going to landfills and reduce costs for clients and the manufacturers themselves? And then in the Bay system, again, we've got this whole dynamic process around landowner access and how do you do this adaptive cleanup in such a big area where there's so much mobility happening. And we anticipate, that cleanup effort, once landowners' agreements are in place, to take anywhere from 5 to 10 years to really fully tackle that 75 miles of shoreline. We'll be doing reassessment and monitoring throughout that entire process, while at the same time continuing to find ways to increase technologies to more effectively remove those plastics. So with that, again, I just want to say thank you for giving us the time today to introduce this kind of new and innovative way of thinking about remediation in a contaminant that's not necessarily a health hazard, but is of increasing public concern, and look forward to your questions. So thank you so much for your time.
Thank you, Ryan and Blake. Great presentation. I know I always get excited to hear about cleaning up the environment. I know we've done a lot of things to the environment to make it either dirty or not as comfortable, not as pretty. And I love to hear about cleanups and helping the environment out. We do have a couple of questions that have been submitted, and I thought I'd just run through some of these now. So the first question here by Dan Crows: what is the typical mechanism of a release? Is it a bag ripping or a conveyor misalignment? I think it's for like a release of the plastics.
Yeah, so typically what happens here that results in this is it's kind of poor housekeeping, at the end of the day. So, again, at least as it relates to that long-term release. So most of the plastics, these pellets, the nurdles, the shavings, or the powder, the way that after production, they're basically piped and blown into rail cars. Sometimes they're piped and blown to the nearest port facility, which these facilities are usually or sometimes very adjacent to. And so you've got these valves that, they attach on, open, and then blow the plastics into a rail car. When you detach that, there's usually some fallout. And if there's not some catchment in place, over time, those gather and collect in the ballast rocks around the rail lines. And then when you have a rain event, they float and flush out and enter your stormwater. It can also be around the actual production mechanisms within the facilities themselves. And then again, during a rain event, kind of float those up and flush them out. So what we're seeing from to reduce things from a stormwater component is, and I can use our client as an example, they're actually using and developing numerous large-scale evaporation ponds that all of their stormwater goes into and then has a filtration tube before it actually leaves their, kind of production security perimeter of the facility and would enter the public environment. They're still working on getting that fully functional, because during a high rain event or a storm, they typically exceed the capacity of that and therefore end up with a release, like I mentioned, that we've had 11 of them. Those have all been centered around high rain events. But yeah, now it's kind of that overflowing of stormwater evaporation ponds, but also poor housekeeping.
Thanks. So another question here we've got is, and I know you've already answered this individually, but maybe you can answer it for the team, for everybody on the call. Do you operate under the Clean Air Act when pre-production plastics are moved through air deposition?
Yeah, no, not with any of the alien transport related to plastics, though, of course, these facilities have to deal with their own Clean Air Act violations and issues related to, any of the other offsets, but not related to the actual movement of plastics themselves.
Thanks. We've got about 4 minutes left here. I'm going to try to run through these and don't want to keep us going too long here. What technique is used in determining the concentration of plastics in soil samples? And does that technique differ based on the size of the plastics?
Yeah, will definitely vary based on the size of the plastic. So, but at the end of the day, it's pretty, rudimentary. So we go out, I know Blake was showing some images of this, but you're doing, basically different depths of carving out cuts so you're doing like a 12-inch by 12-inch by 2-inch deep to identify those nearest the surface. You have a known quantity. You take all those sediments, put them in a bucket of water, make sure you're breaking that all up, dissolve all the sediment so any plastics can release, float to the surface. You quantify those and then extrapolate that to a per cubic foot volume. And our field tablets, and the way that these, we already know what the minimum number is to exceed that threshold. So to save time in the field, if someone's looking at those top 2 inches, we know it has to be 8 plastics. So if they throw that sample in and automatically they see 20 float up, we don't have to spend the time in quantifying all that. That'll be done on the excavation end with the lab. We know, okay, that already exceeded the 8. This is hot. This has to come out.
Yeah, thanks. Here's another question. How effective is, if at all, is vegetation in storing or breaking down the plastics?
Breaking down, not so much. Storing, a major issue, which is why we've got entire places that we call, aquatic vegetation removal areas, AVRAs. It's another acronym we didn't have time to go into today, but some of the kind of floating aggregate communities, such as I think I'd mentioned at one point, alligator weed, smartweed complex, that have these long trailing fibrous root systems, have a high tendency of aggregating floating plastics. And on one hand, it's good because it kind of holds them in that section, but that has resulted in the need to go in and do mechanical removal in places where there's also exceedances. So back to the previous question, we actually do drop samples on those areas within those aquatic communities, extrapolate out the number per cubic foot, and then if it exceeds, we'll go in, boom those off, and then mechanically remove all of that, which in most cases is invasive species, so we're happy to get it out of the system, but it does add effort and does require invasive species removal permits.
Yeah. Thank you. Looks like we probably have about time for one more question on here. I know some others have been submitted. We unfortunately are not going to be able to get to all of them today. Let's see. Here's one question. Considering the nurdles are so floatable, how do you stop or minimize floating nurdles from redepositing on an area that has just been cleaned up? So I guess in your effort to clean up, how do you prevent those from redepositing?
Yeah, so that's typically through those BMP, such as the containment booms. So if an AOC is too large and we're worried about them trailing down a shoreline, we'll segment it into 2 quadrants or 4 quadrants. But you basically, have this boom that goes out there. Both the upland and aquatic portions are removed all at the same time. Before any backfill is done, we skim all the surface waters and do a cleanup using like industrial vacuums along the shoreline itself. And that's when both parties come back in, both the both our client and the plaintiff come in, walk those sections, visually see everything that it's free of plastics before we can backfill and kind of cap those areas. So it's through mainly just those kind of simple BMPs and segmenting it into bite-sized pieces.
Yeah. Okay. No, I appreciate that. And Ryan and Blake, I think we're going to probably have to end the webinar now. We've got, excuse me.
Is it okay if you have time to answer the questions that have already been submitted? Thank you.
Absolutely.
Okay.
I'm happy to go into the chat here and respond back to all of those that we didn't get to verbally address. So I'll work on doing that now.
Perfect. Thank you.
Okay. All right, let's go on in here a little bit. We've got, so you mentioned a little bit about wastewater. Do you think taking a project analyzing the impacts from wastewater treatment plants to bay and wetland systems could follow similar methods, or would it require a different approach, particularly not just the effluent, but the sludge that hosts the majority of plastics?
Yeah, I think there are definitely components of this project that could be applied to that in terms of the sampling. This is kind of one of those cases where we hope that showing effective removal based on the thresholds that we established could be applied as part of a cleanup standard, right? So, I mean, some of the actual approaches could be used as well, but I think it's more getting, sign off on those thresholds to guide those efforts. But yeah, I think the answer is yes, they could definitely be applicable.
Okay. All right. If the pellets consistently float, can a large water tank be used to break up or suspend the sediment and then skim off the pellets after the sediment settles? Then the sediment can be removed and dried and returned to the site. Maybe that's too cost intensive on a large scale. So what are your thoughts on that?
I have a lot of thoughts on that, but I'll try to be really succinct. So there was a cleanup contractor working on this area prior to us onboarding as a remediation consultant that was trying to do that along the banks themselves. And they were using kind of high pressure washing to kind of blast those shorelines, break the plastics out of that would then float down to the water's edge. They'd have it boomed off with, in segments, and then would net the plastics out. And so in theory, you were keeping those sediments within the creek system versus taking them to a landfill. But what it was doing, because you couldn't come back and backfill quick enough, it was causing erosion issues. And so then if you had any kind of rain event, you now have an unvegetated shoreline, and then the flow sweeping down started to create undercuts along the bank. And we didn't want to, given that we've got 3 landowners in this creek system, have to explain to one that was not our client why they might lose land as a result of our efforts. So that's what kind of kept from doing that. In terms of removing it and taking it somewhere else and then redepositing the sediments, that is possible. There's definitely have been discussions about that. But in terms of, efficiency and cost, that's where, you really got to be willing to pay to do that. And what value do you place on those sediments versus just the ability to purchase something nearby and truck it over?
Okay. I think that's all the questions I see here in the chat for now. For those of you who may have additional questions or additional information you'd like to get from Blake or Ryan, feel free to please contact them. Their contact information is here on this last slide, and contact them and with your questions. For those of you still on the call,
would love to hear anything y'all have, or just if you want to set up a discussion about plastics remediation, love to learn from you if you've got your own ideas. So don't hesitate to reach out.
Yeah. Thanks again to Ryan and Blake for the presentation. Great presentation. And we appreciate you all joining us today. Look forward to having you on another Society of Wetland Scientists webinar. Thank you.